In this video, we're going to go ahead and look at one of the three hypothesis tests that use the chi-squared distribution. So the first test we're looking at is called a goodness of fit test, sometimes called a GOF test because statisticians are lazy. And this test is used for claims about a single categorical variable. So goodness of fit tests are used when we have a single categorical variable and I want to compare a theoretical expected distribution to an actual observed distribution for that variable. Meaning somebody went out and collected data for this variable. For example, I might be interested in hair color for students at Shasta College. I could go through and collect a random sample of students and record their hair color. That would be the observed frequency for that single categorical variable. And then using what I know about biology, I could create an expected frequency distribution based on what I know about the dominance of darker colored features for hair and eyes. A goodness of fit test would then look at how well those two frequency distributions match. Are they the same or are they different? This is a hypothesis test, just like we've done the last few weeks, just using a new distribution. So the overall structure of the hypothesis test is the same. It's just those details on how we calculate and phrase things that will change. So for our first step, we're going to state the variable of interest by defining it in words, and then we're going to write our null and alternative hypotheses. And for a goodness of fit test, our hypotheses are the observed distribution matches the expected, and then our alternative is the observed does not match the expected. You should also, if a table isn't given to you, put the observed and expected frequencies into a table. You may need to calculate the expected frequencies. Oftentimes they'll give you probability or percentages or ratio, and you'll have to figure out what these are. And so we'll take a look at how to do this with a couple of examples. After we've listed everything that we're given in the problem and defined our variable of interest, we go on to the plan stage. So we identify that we're doing a goodness of fit test. And in order to do a goodness of fit test, we need to check that all of those expected frequencies that we found in the state step have to be 5 or bigger. So if you go through the state step, you make that table of observed and expected, and one or more of your expected frequencies are smaller than 5, you should stop the test. You should not do a goodness of fit test if you don't meet this requirement. All of the examples on your homework and test will meet this requirement, but you should state that you checked it. Next comes the math. For the do stage, same as all of our other hypothesis tests. Find the test statistic, find the p-value, draw the curve. So we're going to calculate our test statistic. I can talk today. Calculate our test statistic and p-value using our calculator. We're going to draw a labeled and shaded chi-squared curve. For the test statistic, you need to remember that k is our degrees of freedom, and that's number of categories minus 1 instead of sample size minus 1. Because now I'm looking at a categorical variable and I'm interested in how many categories I have, not in how many people I surveyed. The test statistic formula is a sum of the difference between the observed and expected squared divided by the expected. This is gross. I do not expect that any of you are going to do this manually. All you need to remember is what the degrees of freedom formula is and input that into your calculator if asked. your calculator will spit out the test statistic when it spits out the p-value. Once you found your p-value, you're going to draw your conclusion. And remember, that's 2 steps. First, you should write a decision on whether you rejected or did not reject the null, and then write a sentence addressing the claim as it was stated in the problem. So we're going to go through how to find that test statistic and p-value using technology, and then we're going to do a couple of examples so you can see this process laid out. On the TI-84, the very first thing you need to do is put the data in a calculator. So you're going to put your observed frequencies into list 1 and your expected frequencies into list 2. And remember, to get to that list menu, you press Stat, Enter. Once the data's in list, you press Stat, you go to the test menu, and you're going to go all the way down to option D, which should say chi-squared GOF test. There are 2 tests. One's just going to say chi-squared test. You want chi-squared GOF. We are doing a goodness of fit test. It's going to ask you where the observed and the expected are, and it should default to L1 and L2. So if you always put observed in L1 and expected in L2, you should never need to modify this. You do need to feed it your degrees of freedom. So however many categories you had, minus 1, that's what goes here. GeoGebra, very similar. You need a list of the observed frequencies. So A equals curly brackets and then the numbers separated by commas. And a list of expected frequencies. B equals, and then the expected frequencies separated by commas. And make sure they're in the same order. Then all you need to do is call the chi-squared test function, A, comma, B, the names of your lists. Observed first, expected second, just like the TI-84 calculator. The nice thing about GeoGebra is it's going to use this same function call, chi-squared test, for everything we do in this chapter. The only thing that's going to change is the input we feed it. For goodness of fit tests in GeoGebra, it's going to have 2 lists as its input, observed, comma, expected. A reminder that during this do stage, when you draw your picture, these tests are always right-tailed. Almost all of the tests we're doing from this point on are going to be right-tailed tests. When we're looking at those skewed distributions where the minimum is 0, we're always going to be looking at the right tail only. Okay, so let's go ahead and do some examples. I'm going to switch to another tool here. Maybe. There we go. So our first example says employers want to know which days of the week employees are absent in a 5-day work week. Most employers would like to believe that employees are absent equally during the week. Suppose a random sample of 60 managers were asked on which day of the week they had the highest number of employee absences. The results were distributed as shown. For the population of employees, do the days for the highest number of absences occur with equal frequencies during a 5-day work week? Test at a 5% significance level. All right, so we can see that they've given us some data from this sample of 60 managers. And we asked the managers, which day of the week do you have the most number of absences? 15 said Monday, 12 Tuesday, 9 Wednesday, 9 Thursday, 15 Friday. So we can see based on sample data, Monday and Friday seem to be the big hitters, which kind of makes sense. People like longer weekends. And in this goodness of fit test, we're checking, do the differences between these days represent a statistically significant difference? Or based on a sample of only 60, are these close enough together that we cannot statistically state that there's a difference between those days? So we know for the state step, we're going to define our variable of interest. So in this case, X represents day of the week with the most number of employee absences. That's what we asked our managers. We're going to state our null and our alternative. So our null is that observed distribution equals expected distribution. And the alternative is that the distributions do not match. I'm also going to write down, they gave me my significance level, alpha is 0.05. And the very last thing that I want to do during my state step is I want to list the expected values. So this box right here is my observed. That's the actual data we collected. I want my expected. So I'm just going to tack onto this table. Make my life a little bit easier here. And we're going to use what we know about the problem. We know that we interviewed 60 managers. And what we're testing is that do the days with the highest number of absences occur with equal frequencies? So I'm asking, if I ask 60 people, and I know that those 60 managers are going to give answers that are spread out equally among 5 days, that to figure out what goes in these boxes, I'm going to do 60 managers' answers divided by 5 days. And I happen to know that that would give me 12 responses per day if they were occurred with equal frequency. So what I'm expecting, if they actually occur with equal frequency, is 12, 12, 12, 12, 12. And we see on Tuesday they match. On Monday and Friday we're a little bit higher. On Wednesday and Thursday we're a little bit lower. And the question is, does that variation about 12 represent natural sample variation, or is it statistically significant variation? I'm going to state the test that I'm doing. I know that I'm doing a GOF test, and I know that I have to check my expected values, and all the expected values are greater than or equal to 5, so we're good to go. Next, I'm going to do the math. Test statistic, p-value, graph. So I'm going to put my observed in list 1, I'm going to put my expected in list 2, and I'm going to call on my calculator chi-squared GOF test. And I know it asks me, where did I put the observed? Where did I put the expected? What is my degrees of freedom? And we know degrees of freedom is categories minus 1. There's 5 categories, 5 days. 5 minus 1 is 4. And that's going to give me 2 things. It's going to give me my chi-squared test statistic. It's going to give me my p-value. So let's go ahead and do that really quick on our calculator. So to run chi-squared GOF, I know I need to put observed in list 1. and then expected in list 2. I'm then going to press stat. I'm going to go over to tests, and I want to go all the way down to chi-squared GOF. I'm going to hit enter, and you'll notice it asks me, where is my observed, where is my expected, what's my degrees of freedom. And all of that matches what I wrote down, so I'm going to go to calculate, and I'm going to press enter. And it gives me a test statistic of exactly 3 and a p-value of 0.5578. I'm going to go back to that calculation really quick. Stat tests GOF test. And you'll notice when you go down to that last row next to calculate, it also asks you to draw. If you select draw, it's going to draw the distribution and also give you the test statistic and the p-value. So instead of going calculate, if you go draw, it's going to show you what that picture looks like. And we're going to go ahead and sketch that really quick. So I know my p-value is the area in that tail, which is 55.78%, more than half the curve. And we know that because our p-value is greater than our level of significance alpha, we fail to reject. We only reject the null when our p-value is low. So p-value is bigger than alpha, we fail to reject h0. And if I'm not rejecting h0, I go back to my hypotheses. I was asked, do the days occur with equal frequency? That's this here, that's that claim. We don't have enough evidence to reject that claim. So there is not enough evidence to reject the claim that, and then I'm going to copy wording from the problem, that the highest number of absences occur with equal frequencies. So that right there is a completed goodness of fit test. And you can see we did our state step, which is the biggest chunk. I needed to list everything I was given in the problem, figure out both what my observed list and my expected list look like. I then did this plan step, which is I identified that it's a GOF test. And I did the check. All expected values are bigger than 5. My do step is pretty quick. I don't have to do any manual calculations. I just have to state that I'm using GOF and identify that input, and then write down the chi-squared, the p-value, and the picture that the calculator gives me. And then the very last is the conclude. I have 2 sentences. My first one is, because my p-value is less than my alpha, we fail to reject the null. second sentence then addresses whatever my claim was in the wording of the problem. Let's go ahead and try one more. Make sure that we have a feel for how this works. So our next example says a geneticist is studying the gene pattern of eye color in a group of white mice. He observed a random sample of mice from the lab and found that 110 had red eyes, 57 had brown eyes, 32 had pink eyes, and 13 had blue eyes. His model suggests that the distribution of eye color should occur in a 9:3 to 3:1 ratio. Is there evidence that the geneticist's model is not accurate? Use a 5% level of significance. So let's go ahead and tackle this in order. So I'm going to start with my state step. Variable of interest is, we are looking at eye color of white mice. Yeah. I'm going to state my hypotheses, identify my alpha, and then make my table of observed minus expected. Not minus, but and expected. So let's go ahead and do that. We know for the null, we want the distribution of eye color occurs in a, and then they stated a 9:3 to 3:1 ratio, or the distribution of eye color does not occur in that ratio. Matches the expected for the null, does not match the expected for the alternative. We're told to use a 5% level of significance. And then for this table, we're going to go ahead and make it nice, pretty, and labeled because we weren't given one. So we have, looking at the problem, 110 red, 57 brown, 32 had pink, and 13 had blue. So the order is red, brown, pink, blue. Red, brown, pink, blue. So for the observed, we're just going to list what we were given. For the expected, we have to do a little bit of thinking. So off to the side, 9 plus 3 plus 3 plus 1, because that's the ratios. 9 plus 3 is 12, 15 plus 1 is 16. So I know the probability for each of these eye colors. Red eyes occur with a probability of 9 out of 16. Brown occur with a 3 out of 16. Pink occur with a 3 out of 16. Blue occur with a 1 out of 16. So I know the probability that a randomly selected white mouse's eye color is going to fall in each category. Now I need to know how many white mice I looked at. So I'm going to add these up to figure out my total sample size. How many mice did I look at? So we get 110, 167, 197, 199, 199, 209, 212, I believe. Somebody check my math. I guess I can check my math. Yeah, I can do math in my head. And then to figure out how many are in each box, I'm going to take that sample size and multiply it by the probability for that eye color. So 212 times 9 divided by 16, and I get 119.25. You'll notice it's a decimal, and that's okay. It is okay to have an expected value that is a decimal. For the brown and the pink, which occur with the same probability, 39.75. And then for the blue, 212 times 1/16 is 13.25. And much like our last example, those observed and expected values look similar but not exact. This one's really close. These are kind of close. These are kind of close. These are kind of close, but not precise. So the question is this difference due to natural sampling variation for our sample of white mice, or does it represent a statistically significant difference from the expected distribution? So we're comparing two distributions, expected versus observed. That's a GOF test. And we know we have to check expected values. Our smallest expected value is 13. So all expected values greater than 5. So we're good to go. For 3, we know that we're going to put the observed in list 1, the expected in list 2, and we're going to call chi-square GOF test. It's going to ask us for observed, expected, degrees of freedom. We know degrees of freedom is categories minus 1. I have 4 eye colors, so my degrees of freedom is 3. And it's going to spit out our test statistic and our p-value. So let's go ahead and do that on our calculator. Just a quick note. While I was entering this data in the calculator, I accidentally entered a value incorrectly. So when you're watching this video, when I enter 110 into the list, I enter it as 10. And so these values are going to be a little bit different than what you get if you do this correctly. I'm going to post the correct values for the test statistic and the p-value in the notes to this video. Again, if you have any questions, feel free to email me, and shout out to April for catching that. Thank you. And I'm making a note here in this case that my chi-squared test statistic was so big that it's off the edge of the graph. For conclude, we have our 2 sentences. So because p equals 0 is less than our level of significance of 0.05, and when p-value is low, we reject HO. And then for the second sentence, I need to figure out which of those claims we were testing. So if I come down here to the bottom, it says, is there evidence the geneticist model is not accurate? So it was the alternative, that difference that we were testing for. And if I reject the null, I support the alternative. So there is sufficient evidence to support that the geneticist model is not accurate. All right, my hope is that this process feels familiar. We know what a hypothesis test looks like, so this overall structure should feel very familiar. Remember, you're setting up your list of observed and expected. I know that it's goodness of fit because I'm comparing an observed to an expected, and my variable, eye color, is categorical, not numeric. Last reminder, here, for our list of expected, when I put that in the calculator, I put the frequencies, the number of mice out of 212 that I expected to be in each eye color. I did not put the probabilities. So remember that when you're doing a GOF test, that the lists and matrices that we're going to make on our calculator should be counts. They should be frequencies. They should not be probabilities or percentages. The GOF test and the other chi-squared tests we're going to do this week are comparing counts. All right, if you have any questions on what you just saw, feel free to send me an email or drop by my office hours on Tuesday or Thursday. Otherwise, I will see you in the next video.